In preview activity 4.4, we have a water balloon that's being thrown out 32 feet off the ground, thrown up at an initial velocity of 32 feet per second, and so we're given a function to model the velocity of this water balloon. Now what we're going to do first in part A is we're going to come up with a function s of t such that s prime of t is v of t. So in other words, we're going to come up with the position function for this, knowing that s of 0 equals 32. So what we need is a function that has this as a derivative. So as we start to build s of t, first off we want it to have negative 32t here as its derivative. So that means t squared negative 32, and over the new exponent the derivative of this will be negative 32t plus 16t. Now right now s of 0 equals 0, but we want s of 0 to equal 32, so I can just add a 32 onto the end. So here is our function, negative 16t squared plus 16t plus 32. So we have a position function that gives the position of the water balloon as a function of time. Now, at what time does the water balloon reach its maximum height? Well, remember back a few sections, this thing's going to have a maximum height when the velocity is 0. So what we're going to do is we're going to set our velocity equal to 0 and solve, because that's going to be the point where it stops going up and starts coming back down. And that gives us t equals 1/2 second. So at 1/2 second, this water balloon will be at its maximum height. To calculate its maximum height, we can actually plug that into the function s of 1/2, and we're going to get 36 feet. Now, what time does the water balloon land? Well, that's when the height or the position of it's going to be 0. So 0 equals negative 16t squared plus 16t plus 32. This will factor. 0 equals negative 16 times t squared minus t minus 2, or negative 16 times t minus 2 times t plus 1. Now from this we get two solutions, right? T equals 2 and negative 1, but we're not concerned with the negative 1 in this context. So it lands at 2 seconds. It's going to be useful for us going forward. Now part C asks us to look at a couple differences. For instance, s of 1/2 minus s of 0. S of 1/2 is the height at 1/2 second. So that's 36, and s of 0 is the height at 0 seconds, 32, which comes out to be 4 feet, which means from the time it was thrown, the object, the water balloon, traveled 4 feet upwards before it started coming back down. S of 2 minus s of 1/2, if we calculate this, we get 0 minus 36, which equals a negative 36 feet, which is the distance the ball dropped from its maximum height. At 1/2 a second, it was 36 feet in the air. It dropped down to 0. The negative tells us it's going downwards, so that's going to be the distance that the water balloon dropped. S of 2 minus s of 0 equals s of 2 again is 0, s of 0 is 32, so negative 32 feet. This is our total, this is going to be our change in position. At time 0 it was at 32 feet, at 2 seconds when it hits the ground it's at 0 feet, so this is a change in position. So what is the total vertical distance traveled by the water balloon since it was tossed? Well, remember it went up 4 feet and down 36 feet, so it traveled a total up and down of 40 feet. So remember that's the total distance traveled. That's not quite the same as the change in position. The change in position was only 32 feet. So this brings us over to part E to look at the graph between 0 and 2 and see what's going on. So if we graph our function, and then we're graphing v of t equals negative 32 plus 16. So we've got a vertical intercept here at 16, and we're going to have a horizontal here. Remember, we found the velocity was 0 at 1/2, and we're going out to 2 seconds. So we'll say 2 seconds is about right here. So let's see what we have here. First off, let's look at the area of this triangle. So the area of this triangle is 1/2 the base times the height. So 1/2 times the base of 1/2 times the height of 16 equals 4. That's feet. That's the 4 feet that the object, the water balloon, traveled upward that we saw before. Here, let's calculate the area of this guy. And sorry, we're missing the t here. At 2 seconds, we need this value, and plugging it in, so v of 2 equals negative 32 times 2 plus 16, or negative 64 plus 16, or negative 48. So that makes this a negative 48. We know it'll be negative because it's below the x-axis. And this here is 1.5. Well, let's do it as 3/2. So in calculating the area of this triangle, we have 1/2 times the base, which is 3/2, times the height, which is 48. And let's go ahead and keep the negative in there. And so what we're going to have is negative 36. Remember what we saw earlier, the ball dropped 36 feet. So now we can figure out the total distance traveled. 4 plus our 36 is 40 feet, or we could also look at the integral from 0 to 2 of v of t dt, which we know is s of 2 minus s of 0, which is negative 32. And we can see this two ways. We saw it in the differences that we did earlier with the function. Now we're seeing it in the areas. 4 feet plus a negative 36 feet. It's giving us negative 32 feet, which is the change in position of the ball, or the water balloon. Because it went upwards first, and then it went down, its change in position is only 32 feet, even though it traveled a total of 40 feet. So we can see the relationship between the area under the curve, or in the x-axis, and our fundamental theorem of calculus, which we're about to learn about this section.